But well done, guys. I wasn't expecting this kind of discussion that we would be able to do it today. I thought it would take a couple of good, but you really covered it after my discussion today. Yeah. Okay. So Mary, can you see the video now?
Yes.
Or the slides now?
Yeah.
Okay. Just before I begin, okay, Thomas is not there, his group, but who would like to make a presentation? There are 3 more groups. We are 8 students because you have to cover October by the present. And November is a lot about machine learning, guys. Yeah. So Thomas, before I begin with the class, who would give the presentation? Not the week following, we're not having a class, but the week after. And then also the week after, please give me like kind of idea, because I'm giving my class time to you. It's important. And everything that we are doing, well, essentially I was teaching you. So it's the same thing. It's just a different way of learning. So who would give? That's 14. Okay. So guys, 21st is already taken. I would really mark you in my calendar, guys. Okay, and Thomas, you are left on 14. Don't worry. I will work with you. I will work with you, and you can have as many Zoom sessions or personal sessions with me. Don't worry about that. So wherever you are, I can help you build the project. So we finalized 14th Thomas is giving. 21st, Ryan group is giving. Ryan and Jacob, right? Jonathan. I would be happy if I get you right by the end of the class. You would be 28. So Marwa, you are presenting with Sydney on 28, right?
Okay.
Okay. So then we are covered October. Then in November, I'll start distributing little bit machine learning projects for you. And we take it from there. Okay, good guys. We are doing well. Okay. Right. So guys, I think I would cover something very essential. I think I talked in the last class about some of the common PEM foil preparation methods other than FIB. Now, I talked about things using chemicals, and a lot of you, especially in our research group, we do use perchloric acid and methanol solution, and we do a lot of stainless steel etching to them. And it's a very common practice. Anyone who's doing thesis on stainless steel, which you would be, because you are our research group specialty is a lot of radiation effects in pressure vessel steel. And we have developed a methodology on using the right agent, the right quantities, and that works for different type of samples. Other people who are doing things on chips, or anyone who is from electronics background, they would be using silicon samples. And those people are using hydrofluoric acid a lot. I think I gave you an overview for different people in this class, where we have been, going through diffraction contrast techniques and So people like yourself, Thomas, who would be doing a lot of G.B analysis, this is the kind of thickness you would be keeping. Anyone who is doing high resolution microscopy, you would be keeping 100 Armstrong. And for Merve and for Sydney, you would be doing a lot of eels, and you would be keeping around 100 to 500 Armstrong. So you have to see we are going from Armstrong to nanometers. So be careful on the units here. Now, what is the classic difference between a thicker sample and a thinner sample? The main difference comes in a thicker sample, you have a multiple scattering. And that multiple scattering is where you compromise with the information. You can literally control, that's what you are essentially doing. You're controlling the number of scatterings by controlling the thickness of the specimen. And by doing that, you can control the information that you can take. That is why different techniques here, they have different information that you can take. This is all the review, I think. We did it in the last class. Now would come to a very interesting part here. Yeah. So right. What happens is when you are in working with us, especially in our research group, we give you a sample which is a big sample of any shape. It could be a rectangle, it could be a cylindrical shape like this. A lot of pressure vessel steel samples are given to you like this, literally like this marker. And a lot of them are given in terms of a small cubes. Now, what you do is, what I ask you is to prepare a very good TEM specimen out of this big sample. Now, I know these lectures are not sufficient to train you, but should help you with some information that how to do it. And this would be given to most of you as you progress with your thesis. Now, what we do, we take them to machine lab in UTK, and we ask them to give us these small 3mm discs like this, or something. Some people would say, okay, you can take different shapes, but you have literally a kind of a paper puncher that you have in which you punch your material. It is the same way we punch these discs. So these is literally an example that I took from a paper from reactor pressure vessel steel. And now what we do, what do we want? So now it's not as sophisticated as FIB that I can give you a very good quality thin French. And I say, hey, this is totally, this is electron transparent. In this one, I use something that would create a kind of a dimple in the center. So here you see on the image, and with this dimple that we do, we try to first, it's done by electropolishing, that we try to create this dimple. And once this dimple happens, then it becomes very easy to polish it in the center. So what it does, it creates a hole. So where do you do TM imaging? You do just TM imaging in the center of the hole, just at the edges, because you assume that this dimple here, it has already made the sample thin. Then you put jets of your chemical on it, and we got an electropolisher here that creates a hole here. And you analyze your sample at the boundary of the hole, because we assume just at the boundary of the hole, there are some left out thin edges, which contains all the information about the sample. So you would call it's a very primitive technique, but we have no choice, because as someone told me in the last class, with FIB, we create a lot of damage. So we need to have other mechanical or chemical polishing method to create samples. So this is something that we are doing every time in Oak Ridge National Lab. We just take this small specimen and we dimple it. And after dimple it, we can either electropolish it, or there is another technique that we have is iron mill that we used to do in the past. So this was one of, I think I would speak about iron mill in this. Anyone heard about TIPS? Anytime TIPS? TIPS? No. This is another tool that during my PhD, most of the labs used to have it. And it's a technique that we have an argon ion, which simply, creates, it simply mills it in the center of these dimples. So ultimately you have this thicker piece that would be given to you. You would dimple it mechanically, and then either by electropolishing it or by iron mill, you try to create a small hole inside. And then you look at the edges of the hole, and you analyze your sample, and you would be doing it. Anyone who is involved with iron samples, you would be doing it. Now with ceramics, it won't work. Why? So every kind of material has a particular technique. I did PhD on titanium carbide, silicon carbide, ceramics. What happens with ceramics? Why you think this kind of technique is good for metal? Woman eye, first of all, it would be very tough for me to have, such 3 millimeter waves in this. And then dimple it, so you have to grind it to 100 micrometer, my sample would break. 100 micrometer is itself very thin. And then from 100 micrometer, I am just creating something at the center, which is further break. So I don't see the purpose of doing it. So metals, you do it. And we have students in our group that would work also in ceramics. So for you guys, what is the technique? When you go to FIB, you will see some samples will take you 8 hours to finish. Like some of the intermetallic they took, because they were zirconium based. Depending upon the material, the FIB becomes efficient and non-efficient. So now for ceramics, what do? All these things, initially they developed, they were really interesting. This is very simply that you develop by polishing. And what do? So, example, this was your irradiated phase here. And you glue at the irradiated phase or the phase that interests you. You take 2 samples and you want to analyze this part because you created damage from here to here. And you glue this part by any super glue. So what we'll do, you will have a configuration that where you have 2 interesting zones. The interesting zones would be cross this joint in both directions. There where your most information lies, there where your void lies, bubble lies, and your dislocation lies. Now, you will put the sample on a ring like this. And can you imagine the next step? What you want to do? You want to thin them. Now, this is a very thick, it's a paper thick. And you want to make it as thin as your, your parchment paper or whatever. You want to make it that from a thick. So what do? Now, can you imagine? Overall, these are the steps given. You see the samples, you glue them, use a diamond saw. So use a diamond saw to section them. And then it says polish one side first. And you polish them. And you already polish them with a grid sandpaper. You mount them on grid, which is a microscopy grid. Then you have to be communicated when you do it, your sample. So this is an important number that your sample should be before you iron mill it. Other than that, you know what people do? Yanru from our group is doing. We do tripod polishing. In the tripod polishing, we have a polisher which gives a certain angle to your while polishing. And when it gives a certain angle while polishing, you can see certain angle, it would give you a wedge shape kind of a material, and you will analyze at a wedge. Right? Yeah, question. Yeah, that's a perfect example to observe chemical changes. but you won't be disappointed with the phenol fringes in any sample that you take in microscope. You will always have it. Yeah, it's something, it's impossible to have uniform thick sample even with FIB. So this is what you do in iron mill. I would go through this technique. So I think Oak Ridge has iron mills. I have to see if university has it. But we students do a configuration like this. They take it to the tripod. In the tripod, they try to polish it with hand. And when they try to polish it with hand, finally the materials comes out like a wedge shape. Now here, this is another example given to you. So very interesting. If you have thin films, and a lot of places you will have thin films, so you can create cross-section samples like this. So can you give me a practical example where such kind of materials are used? Where you want to observe a thin film. Any practical example that comes from nuclear materials? You can there was ATF project started, and ATF project was something where you do not want your slab to be oxidized at accidental conditions. They started putting coating on that. Yeah, piso particles, stuff like that. And when you have this piso particle or biso particle, that's a fuel particle. Then that's a hybrid particle. Such material we use that. The coating is so delicate. It would, you would be able to just destroy it. Yes.
In like a compact 8,000 price of particles. One or two bits per second. And then they actually come in and do TE and lift out. So I've seen a lot of it.
All these people, they are banging heads and sample preparation. So I think I mentioned to you earlier, microscopy becomes easy and easy to sample. If your sample is not good, you will have very tough time with the microscope. So first, number one art to learn is to prepare very good quality of sample. And you have to work through it. It doesn't come like that because you are literally creating something thin as in thickness about 50 nanometers, 100 nanometers. That's the sample you're looking at. So it's very thin, right? So you are able to destroy it. And this is here, take an example of a BISO or TRISO, where you have this layered material. Someone joined it with a super glue, made a block like this, so that he got multiple chances to see in one sample. And then it becomes a sample, like this, and now he's trying to slice it. And now you got a sample like this, then he said dimple, then iron mill from here. So you got here three joints to work on. And so you multiply your chances to look at things. So here, when I dimple it, some of the things would be broken, which is fine. But then there would be still enough to look. So whenever I used to be in the lab, you have to imagine you're on a football stadium and you have a billiards ball. So if the football stadium is your sample, you're looking through the billiards ball. This is how you just hear that local. And there's a vast amount of land is present, that is your sample. So I'm just talking in terms of dimensions that you understand. So my point is this 3 millimeter in terms of nanometers presents you 3 into 10 raised to power 6 nanometer area, which is big. And so if you even create a dimple here, lose some of the samples, still you will have enough small corners that you will zoom out, and that would be in terms of your nanometer value, and you can take enough value. Right? Now, iron mill. So what happens in the iron mill? it is one of the common thing, very common. We call it tips. It is your sample here, and here's your sample. Some of the experiment configuration, you rotate it. You have a plasma and you have an argon beam coming through it. It's very automatic. You put it into the little sample holder here. You try to give your argon enough energy according to your sample, and that argon beam would slowly get into here and try to slowly erode the sample from center. So overall, it tells you that you can have a controlled sputtering using energetic argon ions, and you have the incident energy between 100 volt and 6 kV. And then he tells you that you can control angle of incidence, current, and voltage. Maximum thinning rate is 14 degrees and 16 degrees, and final thinning done at lower angles. So you would use it in your career. It's a very common technique. Moment you go to example like BSO, TRISO, coated samples, analyzing, doing nano indentation as well, people create such samples. So one of our PhD did nano indentation on it because he wanted information from the transfers part. Pong Pong Cheng from our group. Yeah. So yeah. Energy is very like kV, 6 kV. So in our case, now we are very high. Yeah. 2, that's the final one. But with 30 kV, you give them enough damage in the beginning. Just creating, you're removing it. Now, this is a classical example we have got in JIM in our lab, where I created a dimple and I give a Z. And I put my sample here and I give all those chemicals which we talked about in the first slide. That is basically an electrolyte that is inserted through these pipes. It's nothing, very easy configuration. You have a bath here, you have a pump here and a pipe, and a thin jet that goes on your specimen. Very simple. So two things that you can also DIY at your home. And you have the acid, and with the nozzle size, you can control the jet. And slowly you start eroding the material from here. So I think this is self-explanatory, this slide itself. And generally, this slide mentioned that we use a lot of semiconductors, but in our case, we do it every day on iron-based alloys. Now, there is a summary here. He says that other famous techniques that you would come very easily, whosoever do thesis in microscopy, that you will do tripod polishing. I think I talked about it. Then you will also have nanoparticles and nanotubes and nanowires dispersed in methanol. That was my career in industry. I worked for industry for 2 years in a steel metallurgy lab for a company. And there they used to have these particles dispersed in a liquid. And we used to take a grid and literally fish those particles on the grid. We used to have a carbon grid, and that carbon grid is simply your PEM grid with a wire mesh inside. And you would take the tweezer in the lab, you will take your carbon grid, take it in a sample which has got nanoparticles. And then what would happen as you immerse the grid into a solution with nanoparticles, your grid will take the nanoparticles, some of the nanoparticles. And these nanoparticles, they are actually trapped in this grid. And that's what you take inside your microscope and start analyzing it. Now, then other thing is cleavage. And then there's one more famous technique. Cleavage is something that I think we talked about. We can fracture it. And you can do things along the cleavage plane. So it's something that is a mechanical technique that you break your sample and then you break it and you just analyze the edges around that cleavage. And it says that it's not very common. But this last one, replica, one of the colleagues at Oak Ridge National Lab, if you know, who happens to be working with, there's one student who migrated from University of Michigan to our group. She's senior now. What's her name? Samara. And she works with some of the people in her group where they got funding, Phil Edmondson and others, they got funding on replica. So what happens with replica? You have a sample, you coat it with carbon. Then you take that carbon out. And that carbon, it contains the information about your sample. Because you put carbon here, and carbon it gets deposited. And then what happens is you take it to some chemical that is able to take carbon out of the sample.
As a piece or?
It's a carbon is when you deposit it, it's literally like a paper thin, like this, it's a replica. It's deposited like this, and suppose my surface had precipitate. So it just comes out like this. And there's a technique, and this surface contains precipitate. And they got funding on it to do that. So essentially, just take your sample and deposit carbon on it. And then there are chemical ways to remove that carbon as a layer. And depending on how thick is your carbon, you can play. Okay. Now we come to the next topic, that is electron scattering. This is an easy part, but I will go through it. So you know about different, here there's a small comparison about the nature of electrons, photons, and neutrons. And what we care is about electrons. And we are an electron microscopy, and we want to understand when electron, it gets into the matter, how it behaves with the matter. Now there's a statement saying electron interact very strongly with matter. Now we know that electron, it's a small negatively charged particle. It directly scatters off atom, either nucleus or electron clouds. So this entire presentation would be about how electron behaves with your material. And electron, being a charged particle, would interact with the charges present in your material. And when you imagine it, just to build your thoughts correctly, you have to imagine electrons. You have to imagine that electron gets into a bed of material where there are other charges present. Now, other charges that are present, they are nucleus and electrons. Electrons coming from top, it either would see electrons of your sample, or it would see the nucleus of your sample. It would see both. If you make your sample very thick, then what would happen? You are not doing TEM, you started doing SEM. That is the classic difference between TEM and SEM. You tell me what is the common energy electrons in SEM? What are you using in TEM? Answers the question. 30 keV, a very small energy, and then your sample is thick, you don't care. Simply, what happens is everything is backscattered, whatever information you get. In TEM, you can do both. You can have information from backscattered electrons. Nobody stops you. But you can also have information from transmitted electrons. So this should be very much clear to you, difference between TEM and TEM. Both use electrons. One has 30 keV, other has 200 keV. Also, people go to 1 million keV depending upon your sample choice, your microscopy. So this is one thing. SEM, everything, information come from backscattered. And in other thing, it is coming from transmitted. The electrons are passing through the sample. Now, here, there's a comparison. Basically, what is to me very interesting is your elastic mean free path. For mean free path, you can simply say the path in which your electron travels without interaction. And it does it for only 100 Armstrong. Sorry, 10 to the power 2 Armstrong. Yeah, 100 Armstrong. Why is that? Why it's so slow? Why is like so small here? Free fat is responsible for everything that you see.
Very
It bombards with everything. Then it loses energy. And that is why you have this problem. Other good part about it, so this is not a very good part. Minimum probe size that you can create is 1 Armstrong using electrons as compared to your X-ray and neutrons. Now your absorption length is also very small. It gets absorbed. Just put it electron in your material, you do not see it coming somewhere, right? Now, this is very important for overall understanding what information you can take out from your sample. So, electron scattering is the underlying physics of TEM. And I think we would go more in detail. So there are 3 things. When you are doing diffraction, you will talk about something known as elastic scattering. Whenever you talk about imaging, you would consider both elastic and inelastic scattering. Whenever you talk about spectroscopy, you would talk about inelastic scattering. Does that make sense? So my point to bring this slide is, these are the 3 things that you're doing. So whenever we did helium bubble imaging or whatever, we never talked about losses. We simply consider it as a perfect, which doesn't, a perfect wave, which doesn't do any losses. Whenever I talk about spectroscopy, that would be to take out different information about your chemical composition. You will start talking about inelastic scattering because your electron will have some losses in terms of wavelength and energy both. And imaging, it has both the things involved. Now, this is a classical representation that is provided on the slide. You have incident electron beam, thin specimen, and you get in your TEM, you have a diagram like this. In SEM, everything goes back. All these things are happening. Same time. All these things are your physical phenomena that are happening in your material. So all these things are not very difficult, but it's just a part of this class. I would pass quickly through them. You know most of the terms. Here is our incident KV beam, and it can do 2 things. One is your secondary electron, and other is a backscattered electron. And then what it can do, it can give you Auger electrons, and it can give you X-rays, and also visible light. And we have different detectors present in your SEM especially. And we collect them and take information about the sample by comparing it with your relative sample. Now, in your TEM part, you have elastic, scattered, and inelastic, and you have something called Bremsstrahlung X-rays. Any idea about them? Since I think you are introduced to this thing in your career very early. Breaking radiation. Okay, guys, we are on time. I just don't like that. Go too much behind. Okay, we'll continue with this. So I hope to see you on Monday.
That is, I think that starts at the 3 to 6 o'clock, or what time is that?